Bismillahirrahmanirrahim. In this video, we are going to discuss about the Clarke's transformation. We have previously discussed it in the last video that if we have this orientation, that is alpha axis is like that and the beta axis is leading the alpha axis by the angle of 90 degree, and your phase A is aligned with the alpha axis. So for this particular case, we have derived the transformation matrix, and that is given by this equation. Right, so we have derived it. So for derivation you can refer to the previous video. So in this we have assumed that the theta is equal to 0 and the alpha axis is aligned with the a axis and the beta is leading the alpha axis by the angle of 90 degrees. So for this particular case you will get this equation for the calculation of the alpha component and this equation for the calculation of the beta component from A, B, C. Right, and what is this 2 by 3? This 2 by 3 is basically for the magnitude invariance, that is the magnitude of the space vector in the alpha beta plane is equal to the magnitude of the phase voltage A or the phase quantity A, whatever it is. So 2 by 3 is for the magnitude invariance, so that the magnitude remains same. Now what about if the beta is lagging the alpha axis by the 90 degrees? So if we assume this orientation that alpha is aligned with the axis but beta axis is lagging instead of leading, and it was leading over here that you can see, but over here it is lagging. So if this is lagging, now you should be able to drive the transformation matrix. So you will observe that only these two quantities changes their sign with respect to this one. It is positive over here and negative over here, but in this case it is negative and the positive. Rest of the transformation matrix is same. So based upon the orientation, the transformation matrix may be different and you should be able to drive that one, and for that derivation you can refer back to the previous videos. Okay, similarly we have discussed the stationary to rotating frame of reference transformation in the previous videos, and if I go back to the slides used in that video, we can quickly go through this one. So you can see over here we have transformed from alpha beta to DQ frame of reference, and that is the rotating frame of reference. So in this we have assumed that alpha is lagging behind the beta or beta is lagging the alpha by the angle of 90 degree, and for that we have derived the equations, and with the help of those equations we can find out the DQ component if the alpha beta is known. Right, and similarly over here you can see we derived that if you want to convert the stationary frame of reference into rotating frame of reference, that is DQ, so you will have to multiply with this rotational operator, inverse rotational operator, and from rotating frame of reference to stationary frame of reference you will have to multiply it with the vector rotational operator. Right, so you can do the conversion with the help of this one, where this omega is basically the speed of rotation of your rotating frame of reference, that is the DQ in this particular discussion. Okay, so we discussed in the last video, and then we have also discussed the third case of the Clarke transformation, in which the angle is considered between the phase alpha and the phase Q, where alpha is being considered that it is aligned with the A phase of your ABC frame of reference. So with that the angle is considered between Q and alpha, and the D axis is the lagging one with respect to the Q. So that was the third case of the Clarke's transformation. So with respect to that we have derived at how we can convert alpha beta into DQ, and if you take the inverse of this part you can find out the procedure for converting DQ into alpha beta frame of reference. So now we are going to consider another case in which the beta is lagging behind the alpha. This is the third case of the Clarke transformation, because we are considering the angle between the Q axis and the alpha axis, that is theta Q, but we are considering that the beta axis is lagging behind the alpha axis by the angle of 90 degree. So for this particular case, now if I want to look at the projection, we want to find out the D component. We are converting alpha into D, so we will have to take the projection of this alpha axis over D. So that will be obtained with the help of this angle pi by 2 minus theta Q. So cos of pi by 2 minus theta Q multiplied with the alpha, you will get the component of the alpha along the D axis. So I can say that D is equal to alpha projected along the D and then the beta projected along the D. So basically we are taking this one. So that is shown over here in this equation, that is the projection of alpha along D axis, that is obtained with the help of this angle pi by 2 minus theta Q, and the projection of the beta, along the D axis. So beta along the D axis will be obtained by this angle theta Q. So that you can see over here, cos of theta Q. So now applying the trigonometric identities, you can write down this equation. So let's call it equation 1, and we will be using it onward. Now let's look at the projection of the alpha and beta along the q axis. So I can write down this one, that the net q component is equal to the projection of alpha along the q axis plus the projection of beta along the q axis, right? So that is going to give us this equation, and here you can see that first of all, taking the projection of alpha along q. So alpha along q, you will have to now consider this angle, that is theta q. So cos of theta q, that you can see over here, alpha into cos of theta q plus beta into now taking the projection of the beta over the q. So we will be having this angle. So this is equal to, this angle is pi by 2 and this angle is theta q. So pi by 2 plus theta q, cosine of that one will give you the projection. So this, applying the trigonometric identity, can be written like this. So using this equation 1 and the 2, we can write down this matrix, that is giving us an information that if alpha beta components are multiplied with this, so you will be getting the q and d components. So we call it the transformation matrix. Definitely this will be changing depending upon the orientation of the alpha beta axis and the dq axis at certain instant of time. So for different orientation, this matrix will be maybe different. So for this particular, this transformation matrix is valid. So let's suppose that we are translating the voltage of the alpha beta frame to the qd. So we can write down the equation like that, and in this transformation matrix, that is converting this alpha beta into qd, is given by this part, right? So that we have derived over here. So now if we want to find out the alpha beta components, so alpha beta components can be obtained by taking the inverse of this matrix. So if we take the inverse of this matrix, we are going to get this one. So we can say that this equation is basically like that V alpha beta, that is obtained by taking the inverse of the transformation matrix TQD and then multiplying it with the VQD, that is the voltages in the rotating frame of reference. So with the help of this, you can find out the alpha beta components. So this equation 4 and 5 are for representing the transformations, and in this TQD and the TQ inverse is given by this equation. Equation 6 is representing the transformation matrix, and the inverse of that one is this one. So you can see over here that this inverse is equal to the transpose of the original matrix. So it is the power invariant. So power in the alpha beta frame of reference and the power in the DQ frame of reference will be same. Okay, now let's look at an example in which we will go through step by step to for the conversion. So first of all, we are assuming that VA that is given to us is given by this equation, VB is this one and VC is this one. So we want to represent it in the DQ frame of reference. So first of all, we are going to assume this orientation, phase A, B and C are like this, and the alpha axis is aligned with the A axis and the beta is lagging behind, and we are using the third case of the Clarke transformation because we are considering the angle theta q, angle between the alpha axis and the q axis, and this frame of reference is rotating with speed omega, where alpha and beta are representing the stationary frame of reference. So first step is this one, Clarke transformation. So if we apply that one, so we will have to use the corresponding equation. So we have seen that in the previous slide, if the beta is leading, we have this equation, and if the beta is lagging, we have this set of equations. So in this example, we are going to use this transformation matrix. Okay, so now using the equation of the Clarke transformation, we can write the V alpha, that is equal to 2 by 3 into VA minus 1 by 2 into VB and minus 1 by 2 into VC, and this can be written like this. And similarly, the beta equation for the beta axis voltage from this matrix can be written like this, and from here we can say that V beta is equal to 1 by root 3 VC minus V beta. Okay, the system is balanced. So for balanced system, VA plus VB plus VC will be equal to 0, and there will be no zero sequence component. So from this equation, VB plus VC will be equal to minus VA. So using this one over here, that VB plus VC is equal to minus VA, so we can write down this equation, right? And the V beta beta axis voltage can be calculated with the help of this equation. So VC is given by this equation that is shown over here. right, and the VB is given by this equation, so that is shown over here. So now we need to simplify this one to get the beta axis voltage component. Okay, so now let's simplify this one. So for that we are going to use this trigonometric identity, that is cos of A minus cos of B is equal to 2 sine of A plus B by 2 sine A minus B by 2. So using this trigonometric identity you can go through it. So finally you will get that cos A minus cos B for this particular case will be equal to minus under root 3 sine of omega t plus phi. And the beta axis voltage now can be written like this, because we have evaluated this part, so replacing it with this portion, so you can write down that V beta is equal to this part, and this can be written like that. So we have an equation for the V alpha and for the V beta. Those equations are these ones. So now if you sketch that one, if you look at this part, this is the cosine function. So V alpha, this is the cosine function starting from here and going like that. So this is representing the voltage along the alpha axis, and the beta axis, this is the minus Vm sine of omega t, right? So sine of omega t will be like that, and the minus will be making it like that. So it is minus Vm sine of omega t. So this is the beta axis voltage. So in this case you can see the real part lags by 90 degree from the imaginary part. And what is the real part? Real part is basically the alpha, and the imaginary part is the beta. So the VB is leading the V alpha by the angle of pi by 2, and it is a two-phase balance system when we are going to translate ABC into alpha beta frame of reference, that is the stationary frame of reference. Okay, now let's translate this system into the rotating frame of reference. So now let's look at the orientation. First of all, orientation is like that our alpha axis is along the A axis and the beta axis is lagging behind. So for that we can say that we V alpha minus J V beta, right? So we basically want to work for this one, V alpha minus J V beta, because that will define our space vector in the alpha beta frame of reference. Why minus J beta? Because we are considering beta, this beta is positive over here, that is lagging behind the alpha axis. And if you look at the x-axis reference and the y-axis reference, so this is at the negative part of the y-axis, so we will be considering this part as the negative one. So we are going to work for V alpha minus J V beta, that will be representing our space vector in this alpha beta frame of reference. So with this orientation, now if I write down the equation for the conversion, we need to find out V alpha minus J V beta. So that will be equal to Vm into cos of omega t plus phi plus J into Vm into sine of omega t plus phi. So from where we have got this equation? From here. Here you can see alpha and beta are defined. So I have picked this one. We have alpha, V alpha, and that is equal to V beta. So we can write down this equation, and from here I can say that I can simplify it. So let's quickly do it. Vm into cos of omega t plus phi plus J into sine of omega t plus phi, and we can write it like that this is Vm into e raised power j omega t plus phi, right? And I can also write it like that this is equal to Vm into e raised power j omega t into e raised power j phi. So what is this phi? This phi is basically the phase, and it is a constant one. So this part is constant, right? And what is this omega? Omega is the speed of your rotating frame of reference, right? So this you can say is the vector rotation that we have already discussed in the previous video. So we can represent that this V alpha minus J V beta like this. So our space vector will be represented by this one. So I am going to mark it this space vector. Okay. So what will be the magnitude of the space vector? That is Vm. And here you can see what was the magnitude of our phase A or phase B and phase C voltage. If you look at over here, this is Vm, Vm, and Vm. So it is magnitude invariant, right? So magnitude invariant transformation. Now what is the next step? In the next step we are going to convert this one into the rotating frame of reference. Okay, so converting from alpha beta to DQ frame of reference now. So which orientation we are going to use? We have seen the equations in the previous slide over here in this, right? So here you can see that VQ, the voltage equation for the Q axis will be given by this equation, alpha into cos of theta Q minus beta into sine of theta Q. So we are assuming the voltages. So this will be VQ, V alpha and the V beta. So we are going to use this equation. So now let's move on and write down this one. So we can say that VQ is equal to V alpha into cos of theta Q, right, minus V beta into sine of theta Q. So we have derived this equation earlier. Okay, now we are going to work out for the VQ now. So VQ can now be written as we know the expression for V alpha. So V alpha, if we go back to the previous slide, that is this one over here, you can see Vm cos of omega t plus phi, right, and the V beta is this one. So now using these ones over here, so I can write it like that, that this is Vm into cos of omega t plus phi, that is the expression for V alpha, into cos of theta Q minus now the expression for V beta. So V beta is Vm into sine of omega t plus phi, right, into sine of theta Q. So we have taken the expression for the alpha and beta from this slide. Okay, now we need to simplify this one. So simplifying, you will get this expression. So you can see this expression, right? So Vm into cos of omega t plus phi, cos of theta Q plus sine of omega t plus phi plus sine of Q. So this has become plus, because if you look at, if you go to the previous slide, here it is the negative one. So that's why this negative sign from here has become the positive. So what is VQ? VQ is equal to Vm into cos of phi. So phi is constant one, it's a phase angle, right? So we have the constant voltage in the we have the constant component of the voltage along the q axis. Now let's work out for the dx is equation, dx is voltage. So for that we can write down the equation that Vd, that is equal to V alpha into sine of theta Q plus V beta into cos of theta Q. So this is from this slide, this one. So here we are going to pick up now equation for the dx is voltage, and that is this one, alpha into sine of theta plus beta into cos of theta. So using this equation, we can write it like that, that Vd is equal to Vm into cos of omega t plus phi into sine of theta Q, that is the value of the V alpha, minus, now let's look at the value of V beta. So that is plus, that is minus Vm into sine of omega t plus phi into cos of theta Q. So we have this equation. Now we can further simplify it and we can write it like that, taking Vm common out, and we can write it cos of omega t plus phi into sine of theta Q minus sine of omega t plus phi into cos of theta Q. And then applying the trigonometric identity, we can write it like that, that sine of Vm into sine of omega t minus omega t minus phi. So this can be written as Vm into sine of minus phi, and finally we can write that this d component will be equal to minus Vm into sine of phi, right. So this is the d axis voltage. So now we have translated from the alpha beta frame of reference to the dq frame of reference. So I am going to write down the two equations which we have obtained. So let's take a different color. Vq is equal to Vm cos of phi, and the Vd is equal to minus Vm into sine of phi. As phi is constant, right, so this will be a constant voltage and this will also be a constant voltage. So now how we can represent it in the dq frame of reference? So in dq frame of reference, you can say that our q axis voltage is this one at any instant of time. That will be a fixed one, that is this under root 3 by 2 if phase is equal to, let's suppose, 30 degree. So if we assume that at phi is equal to 30 degrees, so for that I can say Vq will be equal to under root 3 by 2 and Vd will be equal to minus 1 by 2. So depending upon the phase, we can draw the d axis and the q axis voltage, and I am going to assume that Vm is equal to 1. So if Vm is equal to 1, then Vd will be equal to under root 3 by 2 and Vq is equal to under root 3 by 2 and Vd is equal to minus 1 by 2. So this will be representing your the q axis voltage, and if I sketch the d axis voltage, so that will be the negative 1 and that will be equal to minus 1 by 2, constant minus 1 by 2. So that you can see over here, minus 1 by 2. So the three phase voltages, those were the sinusoidal functions or the cosine functions, are appearing the constant ones in the dq frame of reference, because the dq frame of reference is rotating at the same speed at which your voltages were changing in the time domain. Okay, so or the space vector of your ABC frame of reference was rotating. So constant quantities in the rotating frame of reference, so that is very important. Rotating frame of reference has constant values for ABC frame of reference. Why? Because the space vector and the rotating frame of reference are rotating at the same speed. So this gives you an idea that if you have sinusoidal functions, as you can see over here, when you translate them into the two-phase system, you calculate V alpha and the V beta and you represent them in the two-phase system, those are the sinusoidals. This V alpha is basically the variation of the voltage along the alpha axis, and this is the variation along the beta axis. There are two sinusoidals and the resultant space vector rotates over the circle, right. So our space vector will be rotating over the circle in this alpha beta plane. This is, let's suppose, alpha, and in this example we have considered the beta lagging behind. So beta axis is this one, this is positive beta. So our space vector will be rotating because we have two sinusoidals. One sinusoidal is changing its position along the alpha axis, and it is changing its magnitude along the alpha axis, and the other sinusoidal is changing its magnitude along this beta axis. So the resultant is the space vector that is rotating in the space, and that space vector is rotating at the speed equal to the speed of your rotating frame, that is this d axis and the q axis. This was rotating at speed omega, and the space vector, because of this one in the alpha beta plane, will be rotating at this speed omega. that depends upon the frequency of your ABC frame of reference, right? So you have rotating frame of reference. So in that rotating frame of reference, your that space vector is representing as a constant one along the q axis and the d axis. So why we use this transformation, later on we will see in the drives that when we are going to design the PID controllers or the PI controllers, so if we have the constant inputs in the system, in the feedback loops, D and Q axis are the values over here are constant, so you can easily design the PID controllers other than looking for the sinusoidal variations. So these transformations will be helpful in implementing the drives. So if I conclude this video, we have seen a detailed example at how we can translate an alpha ABC into alpha beta and then into DQ frame of reference, and we have seen the Clarke transformation and different orientation of the axis. So for different orientation you will be having the different transformation matrix, and then we have seen stationary to rotating frame of reference. We have already covered it in detail in the previous videos, but here we have taken another example in which the beta is lagging behind the alpha axis, and then we discussed this example and finally represented our ABC frame of reference data in the DQ frame of reference. So that's all from this video. Thank you very much.